Hi, I'm Donald Risostomi and I will be talking about task singular vectors, or how to reduce task interference when doing model merging. So, in model merging, our goal is to merge different checkpoints of the same pre-trained model, fine-tuned over different tasks. Here, one of the most effective approaches is to take the difference between the fine-tuned model and its pre-trained base, and we call this one a task vector. Then, if you sum these task vectors together and sum them back to the pre-trained model, you obtain a model that can do all the tasks at once. Unfortunately, however, you also have to account for task interference. So what we do in this work, we trade the traditional view of task vectors as being flat vectors in a very high-dimensional space with a layer-wise point of view. In practice, we consider the per-layer task differences and call them deltas. And when these ones have a metric structure, we study their singular value decomposition. We see here that these are extremely low rank, with a fraction of the most important singular vectors and values allowing to recover almost all the accuracy. We also see that these singular vectors coming from different tasks interfere, as they are far from being orthogonal. So our approach first leverages this low-rank property by performing a low-rank approximation of the deltas. Then we orthogonalize the task-specific singular vectors, or TSVs, to reduce the task interference that we've seen. After we do this, we can sum across all tasks the TSVs properly weighted by their singular values and obtain our multitask delta. This one can be finally added back onto the pre-trained model to get the final merge model that we wanted. We can see here that this results in a gain of more than 10 accuracy points with respect to vanilla task vectors, allowing us to establish a new state of the art by a large margin. This is consistent across all benchmarks and architectures that we tried, scaling well from 8 to 14 to 20 tasks. Finally, when we do know what task we are dealing with beforehand, we can use the low-rank approximation of the deltas for compression. This results in a model with more than 99% of the original accuracy across all tasks, while having less than 10% of the storage required to keep all the different fine-tunings at once. We see here that TSV effectively reduces the interference that we've seen simply as a heat map before. In fact, this can be easily measured, and if we do this, we see that it is high for shallow layers, that are usually more general, and lower for deeper layers that may be more task-specific. Here we can also see how the reconstruction error from the orthogonalization process is way higher when orthogonalizing all the singular vectors, and not only the most important ones, possibly explaining why low-rank approximation is beneficial in the first place. Indeed, as we can see in the ablation study, while low-rank approximation alone actually worsens the merged model, this brings the best results overall when coupled with interference reduction. So, summing up, in this paper we merge models by low-rank approximating per-layer task vectors and orthogonalizing their singular vectors across tasks. This way, reducing task interference. Thank you.